morning, good morning. Mr. Lesham is here. Guys, thank you. We are continuing with calculus. We are still working with graphs, but yeah, it's a little bit different. I don't know if you're going to find it easy, hard, I don't know. But what I can tell is if you're doing science, who's doing science? That is quite, not many of you, eh? This is quite important for science. So when you did things like motion of an object, accelerating object, or when you're doing, I think, EMF, Faraday's law, do you do that? Yeah. The flux, the relationship between the flux. So very similar question to that. So what we're going to do is, we're going to look at the graph of the derivative. So far, we had a function. Okay, let's say we had a function, in this case a parabola, and we might have calculated the first derivative of that formula in different places. But what we're going to do now, we're actually going to take this function and plot the derivative, the function of the derivative. So the derivative itself is also a function. I mean, just giving you well, let's just do it. So let's say I have a function, yeah, let's just draw that. So let's say we have x squared plus 2x plus 1. Okay, I'm not saying that this actually looks like that, but just to give it a certain function. What will be the derivative? 2x plus 2. So all I'm saying at this point that the derivative itself is also a function which we can then plot. Okay? Now, that's all I'm going to say now. Now, well, then I'll say it now. So if the function of this, or the graph of this function is a parabola, as it is for quadratic function, what will be the graph of the derivative? What kind of graph is this going to be? It's a straight line. Okay? So the derivative the graph of the derivative of a parabola is a straight line. Okay? And I've put the derivative, I made this graph cross the x-axis. In other words, the intercept at exactly places the same as the stationary. And that's not a coincidence. That's always going to happen. Okay? Because what is the gradient here? What's the derivative at this point? 0. It's 0. Therefore, the derivative, the graph of the derivative must cross the x-axis because the value here should be 0. Okay? It's always going to be the case. A stationary point on the function, on the graph of a function, is going to be an x-intercept in the graph of the derivative. We're going to write it down in a second, so don't worry about it. Okay? Now, I want you to see again, to try and convince you why this is the case. Over here, before the stationary point, what is the derivative here? It's negative, and you can see, yes, the derivative here is negative. Okay? This graph tells you what's the derivative. At the stationary point, the derivative is 0. After the stationary point, what is the derivative here? Positive or negative? Positive. It's positive, and you can see it's positive. Okay? So maybe now, yeah, I'm just going to pause here just to save some time. What I've added here, guys, is just what I told you, okay? That the graph of the derivative, the graph of f prime, has an x-intercept where f has a stationary point. So, I'll just pause, yeah. Just to kind of explain what Simon said. Simon said, if the value of the stationary point, the x value is, let's say, 2, 1, or whatever, okay? Then that means the gradient here is going to be 0 at x equal 2. This is going to be x equal 2. Now, obviously, this is completely nonsense what we wrote here, because this is, you know, and when x is equal to, this is definitely not 0, isn't it? So I just made up some kind of function. I'm just going to get rid of it, because I just wanted to give you an idea, okay? But you are right. Wherever the stationary point here, that means that the derivative is 0. Okay? Maybe I'm going to give you a number that does work. So let's say, you know, that, for example, could be an x minus 2. So when x is equal to 2, that's going to be 0, right? Now I'm going to do something that you don't know how to do it. Okay? X squared over 2 minus 2x plus 1. That could be, for example, place. Okay? but then this is not 1. I'm not going to draw what this is. Just to make it confusing you a little bit. Never mind. Alright, let's look at this. This is another problem. My question for you is, what would the graph of the derivative look like? I'll pause and see if you can come up with an idea. Getting some correct answers here from Taylor. It's also going to be a straight line. Okay? Graph or derivative of parabola are always going to be straight line. You can see it because what is the graph of a parabola? The graph of a parabola is always ax squared plus bx plus c. Right? That's the most general parabola. Okay? Now if I do the derivative of that, what will be the derivative of that? 2ax plus b. Well, that's the graph of a straight line. Okay, so it's always going to be a straight line. But Taylor's saying now it's going to be a line going downward. Why is it going to be a line going downward? Because what is the gradient here? Is it positive or negative? Positive. And the gradient here after the stationary point? Negative. Okay? So that's the difference. Okay? Let's see if there's anything I need to add. Right, guys, so that was pretty easy and straightforward in parabolas, quadratic function. But obviously, you know, in grade 12 we work a lot with cubic function. Okay? And we know that this is the typical shape of cubic function. Okay? Let's see what we know. What do we call these points? What are these points? Stationary point. I'll call them SPs. Okay? And what is that point in between? This one. Point of inflection. POI. Okay? And now the question is, okay, if this is a graph of a cubic function, what will be the graph? Okay, so this is a cubic function. What will be the graph of the derivative? It will be parabola. Good guess. It will be parabola. Now, to kind of see it a bit better, there's two ways. I'll start with one which to me seems to be a bit easier. Is just do the derivative. So let's do the derivative of that. What would that be? 3ax squared plus 2bx plus c. Well, yes, you know, that's a quadratic function. So, of course, it's going to be a parabola. But the question, what kind of parabola? Is it going to be a smiley face or a sad face? Okay? So, obviously, they're going to have two situations. Let's start with that. Maybe the first bit to do is to ask ourselves point by point. Okay? What will be the gradient here? What will be in the derivative here? At this point, what will be the derivative here?
0.
It's 0. So this is going to be an x-intercept. We said it already. I shouldn't have erased it. A stationary point on the graph of the function is a 0, is a root on the derivative. That means this is going to be also 0, right? So this is where it's going to cut. But right now we don't know if it's going to cut like this or cut like that. Oh, sorry, or cut like this. We don't know, right? So we're going to ask ourselves, before that, what is the derivative here? Positive or negative? It's positive. So that obviously should have been going like this. What's the derivative between these two stationary points? It's negative. So this definitely is going to go down. Right? And also here, this is going to go down. What's the derivative after the stationary point? Positive or negative? Positive. So you're right, Taylor and others who said that this is going to be a happy smiley face. Okay? Now. Okay? What is the point of inflection here? What do we call this point of inflection here? Is this bit? What do we call this bit? What is that?
Turning point.
It's a turning point or a stationary point. Okay? So that's a stationary point on the derivative. In other words, let me just pause, make it a bit short. So what did I write here? The first bit we already know from the parabola case. The derivative, the graph of a derivative have an x-intercept where f had the stationary point. Okay, stationary point basically means derivative is 0, so that's the x-intercept on the graph of f prime. But now we can see that the stationary points on the derivative graph correspond to the point of inflection. If you look at this, the point of inflection We never really mentioned that, but the point of inflection is where the graph is the steepest between the two stationary points. Can you see? If you imagine you are on this cool little slide, okay? You guys go to these water parks, or you're too old for that now?
Never too old, sir.
Yes.
Never too old.
Okay? So, you know, you go, whee, okay? When you hit the point of inflection, that's where it's like, okay? After that, it becomes more gentle. Before that, it's a little bit more gentle. So the point of inflection have the steepest gradient, means the gradient is the most negative in this case, okay? So, wherever f has stationary point, it has a stationary point, f prime, where f is a point of inflection. Let's try and draw this. Okay, I think you guys can probably guess. If this is a smiley face, what are we going to have here? A sad face. You can say sad face. It's okay to be sad. Okay. Alright? Alright. Let's try and understand. Again, a stationary point here means that the gradient is 0. The derivative is 0. Stationary point here means the derivative is 0. Right now, if you look at the point of inflection, that's the steepest positive part. Okay? If you were to climb, what are we climbing here? Lady Slipper. Okay? So that's the hardest bit to climb. Do you have to climb big mountains in the way?
Sure.
Which one was the worst one? Was that in the first, in the, what do you call it, Leopard's Trail? Was that where there were big...
Yeah.
Our group, we took the wrong path. It was literally when we looked on
Yeah.
and it is when you climb up, so there was no fall. You fell down the.
Is that the Leopard's Trail?
You would die.
Yo.
Because we had to grab onto little bushes.
With the backpack? Yeah. So the point of inflection, if you look at it, is the steepest part, the most positive gradient, as it should be. Okay? Maybe I'll try and draw it a little bit better. Okay? So the steepest part is over here. Okay? Right, I'll pause and let's do our first example. So what we're going to do now, this could be a question. I don't know if it's level 2, level 3, I don't know what it is. We've got a curve, parabola, and we asked to draw or sketch, a rough sketch of the derivative of that formula. So we already know in our head, okay, that's a parabola, so what kind of graph am I going to draw? What shape is it? It's going to be a straight line, right? Now, the next question you got to ask, is it going up or going down?
That one.
This one, for this one, is it going to be going down or going up? It's going to be going down. The way to think about it, I'll just show you. You ask yourself, okay, in the beginning it's positive. I'm doing plus for meaning showing that the gradient is positive. Even below here, I know the graph is negative. I mean, the function is negative, but the gradient is positive. So it's positive all the way to here, and then it goes negative. This is maybe one way of you can do it. So it's going to be a straight line. Okay, starting from positive value and then become negative value. Okay, it's positive gradient here, negative gradient. And then the last bit I need to add, what do you think I need to add? Right now I'm missing one mark. The x-intercept. What is the x-intercept? That's it. I need to just put -3. Because at -3 it's exactly 0. Still need to, where's Eugene?
He's also
Okay. Oh my goodness, okay. Alright, I need to still ask Mrs. Funny-Kirk about that thing. We've been increasingly.
So why?
Let me just pause, So, Ollie's asking, what about the y-intercept? There's no way of us knowing it. Because we're not given the function. It's just a rough sketch. Okay? Right, next thing we're looking at that. Okay? So now we know that almost said that. What kind of line are we going to draw for the derivative if I have a cubic? It's going to be a parabola. But is the parabola going to be a smiley face or a sad face? Yeah, you're right. It is going to be smiley. How do I know that? Because again, I'm going to go with this. I think this is quite a good one. So what I'm plotting is whether the gradient is positive or negative. It's positive, right? So I'm going to do positive, positive, positive all the way. Here I'll put 0. Now it's negative, 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 0. And then it's positive, positive, positive. This is probably the best way. Okay? So I know I'm drawing a parabola. I have to start with positive. So it's going to be positive. Okay? And then at some point, okay, it needs to be negative and then positive again. Okay? Now, it looked like, and I'm going to just change it, it looked like it was going through the origin. It actually didn't. It was just somewhere. So now I need to put some values, right? Let me just check that by the way I'm right. Okay. What's going to be the value of the x-intercept here? Minus 1. And the x-intercept here?
2.
2. Okay? Because the stationary points are again your x-intercept. Now, they do want me to find out what this is the point of inflection. But they didn't tell me what my point of inflection. So how can I still tell where's my stationary point here? How do I know what that is? We spoke about that. We've never really actually done it, but I told you. Yeah? The middle value. Okay, so normally to find the point of inflection, I have to find the second derivative, make it equal to 0. I can't find the second derivative, I don't even know what f of x is. I just got a drawing. But I know the point of inflection is always between these two values. So what's in between? We can add it together. 3 divided by 2 is 1/2 is going to be half. Okay? You understand what I've done here? I just did 2 plus 1 is 3. That's the distance. Divided by half. Divided by 2 is 1/2. So I know I'm 1/2 on each one of those. Okay? I'll pause here. Do as much as we can today. This is a more complicated example. What we did now is pretty basic. So they're giving me a graph of the derivative. Not of the function, of the derivative. And they're asking me what is the gradient of the tangent to f at x equal 0. Okay, I'll read it again. This is the graph of the derivative. Using this information, what is the gradient of the tangent to f, not to f prime, at x equals 0? It's a complicated way of asking you what is the derivative of f at x equal to 0. It's the same thing. What is the derivative of f when x is equal to 0? Minus 4. Okay? So look, we've got some kind of graph. Okay, this is f of x. This is the derivative. The function itself looks something like that. And at x equal minus 4, the derivative is 0. At x equals 0, the derivative is minus 4. I'm not really helping you now in mind. Let me try again. What is the gradient of the tangent at x equals 0? Why are they leaving now? Yeah. What is the gradient of the tangent at x equals 0? Let's say this is x equals 0, right? Let's say this is x equals 0. Okay? Now we're going to have a tangent here, right? The tangent will have a certain gradient. How would I know what the gradient is? Well, I will figure out the gradient because the gradient is the same gradient of the value of the function. Well, what's the gradient at the function when x equals 0? You just read the derivative. The derivative at 0 is minus 4. You just read it from the graph. Okay? Let me just pause and see what's up with these dudes. Go. Okay? Let me try again. I've got some kind of function with a graph. I don't know, I wasn't given that. Okay? And I'm asked at a certain point, x equals 0, to find what's the gradient of the tangent. Well, the gradient of that tangent is the same as the gradient of that function. Do you agree with me? That's what the tangent is. It has the same gradient as the function itself. So they really asked me what is the gradient of the function at x equals 0. Well, this is the graph that tells me what's the gradient. What is the gradient? What is the value of this when x equal to 0? Minus 4. Okay? So the answer is minus 4. It's a bit tricky. Next, write down the x coordinate of the stationary points of f. Okay? Do I know that? Okay. Where would I have stationary points of f? I'm looking for these points. These are my stationary points, right? And I'm looking for both of these coordinates. What are they? Good. Okay. In fact, except that I should have had a minus there. That doesn't make sense. Yeah. Okay. So all he's telling us, no problem. Okay. Look over here. This is the graph of the gradient. The graph of the gradient is 0 at minus 3 and 1. That means that the stationary point on the graph are going to be at x equal minus 3 and x equal 1. These are my two stationary points. Okay, I'll just pause here. Next thing, they're asking me what's the gradient of f when x equal minus 2. X equal minus 2. Now I'm not seeing minus 2 here. How can I read it? But where is minus 2? It's exactly the turning point. Okay, this is minus 2. So it's going to be in between those. Okay? Now I'll just pause here for a second. Okay, so obviously I made a mistake. Thank you, Simon. Minus 2 is not in the middle. Minus 1 in the middle. So minus 1 is your stationary point, which means it's a point of inflection. Now they're asking, what did they ask me? X equal minus 2. So x minus 2 is here. Now, I'm not going to ask you, I'll just show you how you do it. Okay? Obviously this graph is symmetric around this line, right? There's a symmetry. Okay? You understand what I'm saying? So the value of here is the same as the value of here. The value of here is the same as the value here. The value of here is the same value as there. So minus 2 is 1 away from the stationary point, exactly the same as 0 is our minus 4. Okay? Yes, it's a difference. So the gradient at minus 2 is the same as the gradient here. In other words, it's minus 4. Okay? The derivative at minus 2 is the same as the derivative at 0, meaning it's minus 4. It's a little bit of a, quite a bit of a difficult question. Guys, they're asking us for which values of x. This is kind of similar to what we did with graph interpretation. Looking at the graph of the derivative, for which values of x, f is increasing. When is f increasing? What we're going to ask ourselves, when is the gradient positive, right? F is increasing, okay? When f is increasing when the gradient is positive.
Smaller than minus 3 or bigger.
Good. So it's going to be x smaller than minus 3. Before minus 3, the gradient is positive. Not the gradient of this graph, but the gradient of this graph. Or larger than 1. Are we going to include the 1 and minus 3?
How about
now? They are including the stationary points. Highly annoying.
How about now?
Okay, we're including their stationary point. Because you remember, in the stationary point, it's increasing and decreasing. Still need to sort it out for you guys. Okay, so we are including that. When is this graph decreasing? When the gradient is negative, that means between minus 3 and 1. Okay, so it's going to be larger or equal to minus 3, smaller or equal to 1. Just going to check, yeah, we're fine. Okay. Next question is f concave up or concave down? Okay, concave up or concave down at x equals 0? That's a tough one. At x, let me just pause. Okay. Right, very, very difficult question, guys. Very, very difficult question. I'll repeat the question. Okay? They're asking me if this graph, the f, is concave up or concave down at x equal to 0. Now, to remind you and remind myself, okay, to find the concavity, what we're going to do is find the second derivative. If it's larger than 0, that means it's concave up. If it's smaller than 0, it's concave down. Let me just check that. Check for me. Is this right what I'm saying?
Yes.
Is it different? Let's just check that. Must trust them. Guys, bear with me. We'll finish it up. Okay? So what was I saying here? Right. In this case, what is the derivative of the first derivative? Because second derivative is a derivative of the first derivative. This is the first derivative. What is the gradient here? The gradient is positive. Okay? That means it's larger than 0. That's why it's concave up. Okay? I will pause here. Okay? I'll give you homework and we'll finish this lesson. Okay, so you guys are already gone, but I'll finish this question here. So in the last bit, we are asked to draw the graph of this function. Okay? And what I would do is I would start with identifying the stationary point and point of inflection. So the stationary point, okay, that's a stationary point, right? We said an x-intercept in the derivative, the graph of derivative is a stationary point. So I'm going to draw that here. Okay? That's at 3. There's another stationary point at x equal 1. Okay? But obviously it's not in the same place. Now, so I'm just going to draw it for now. I'll draw it here. Okay? Now, the question is this a maximum or a minimum? So the best way, as I showed you before, to me, to look at it is, I'm plotting on the derivative. What is the derivative? Derivative is positive here, and then it's negative there. Okay, the derivative is positive before and negative after. So that means that before the derivative is positive, after it's negative. So it's going to be a maximum. And then therefore that really has to be a minimum. Okay? Now I'm going to start by drawing it here. Okay? The same, why? Because here, I'm not sure how much you lost, so I'll just repeat again. So by looking at the derivative before, which is positive, and a negative after, I realize this is a maximum. In the same way, the derivative here is negative and positive after, so it's going to be a minimum. But if I draw it like this, then, I mean, these lines cannot meet. I mean, I cannot draw just a line that goes like this, yeah? Because that means I've got another stationary point, okay? So what I have to do is either pull him down, okay, or push him maybe higher up. At this point, to be honest, there's no really way that I know. But what they told me is, and I didn't read to you, is that I know that f of x is f of 0 is equal to is positive. So if at x equals 0, the derivative here is not derivative. The value of a function is positive. So that means I need to pull that one down. I'll pull that down like this. Okay, and I'll pull him a little bit up. And then what we're going to do, oh, this is a terrible drawing. Okay, I'll try and draw it. Okay, so it's going to be like this. Struggling here. Okay, and then we're going to have some kind of point of inflection. Okay, and then whoa, so it's going to be something like this. And like that. Something like that, okay? Now I just need to put the values again, because I erased them. This was 3. This was 1. Okay, that's a stationary point. And the point of inflection, as we found out, was -1. Okay, cheerios, bye-bye.